There is a specific kind of silence that falls over the bridge of a warship when the radar tracks an unknown contact, but on the USS Gerald R. Ford, designated CVN-78, that silence is underscored by a different sensation entirely. On previous generations of aircraft carriers, the ship felt alive with the mechanical groaning of steam pipes, the shudder of hydraulics, and the physical vibration of massive pistons driving catapults. The Ford is different. It is unnervingly quiet, humming with an electrical potential that feels less like a ship and more like a floating power plant. This vessel, the first of its class, represents a $13 billion gamble by the United States Navy. It is the most expensive warship ever constructed, a price tag that has drawn ire from Congress, mockery from critics, and deep concern from military strategists. But to look at the price tag is to miss the fundamental conflict at the heart of this machine. The central mystery of the Gerald R. Ford is not whether it can float or launch aircraft, but whether the very technology designed to make it invincible has actually made it fragile. We are looking at a vessel that attempts to replace 50 years of proven brute force steam mechanics with digital electromagnetic precision. It is a transition as significant as the move from sail to coal, and it has been plagued by a development history so fraught with failure that, for a time, it seemed the ship might never be combat effective. The Ford was built to solve a problem that the legendary Nimitz class could no longer answer: the need for raw electrical power. But in solving that problem, the designers introduced a level of complexity that threatened to turn the Navy's greatest asset into a floating paperweight. To understand why this ship exists, you have to understand the crisis of the early 2000s. The Nimitz-class carriers, the backbone of American power projection since the 1970s, were hitting a hard ceiling. They were not running out of hull life, they were running out of electricity. A Nimitz-class carrier, for all its nuclear might, is essentially a steampunk machine. Its reactors boil water to spin turbines, and that steam is piped physically through the ship to drive the catapults. It is a messy, maintenance-heavy, and inefficient system that leaves very little surplus energy for modern electronics. The Navy looked at the future of warfare: lasers, directed energy weapons, massive radar arrays, and realized the Nimitz could not power them. They needed a new hull, one designed not just to carry planes, but to generate and distribute massive amounts of voltage. The result is a ship that looks deceptively like its predecessor. From a distance, the CVN-78 shares the same gray, flat-topped silhouette as the Nimitz. It is 1,106 feet long and displaces 100,000 tons. But the resemblance is strictly superficial. Underneath that flight deck lies a complete reimagining of naval architecture. The designers did not just upgrade the systems, they ripped out the industrial heart of the aircraft carrier and replaced it with a digital one. This decision sparked a decade of controversy, budget overruns, and public failures. The central conflict we must explore is whether this radical leap was a stroke of genius or a case of technological hubris. If detailed technical breakdowns of military design and strategy interest you, subscribe. I have got more of these coming. The first thing you notice when analyzing the design philosophy of the Ford class is the flight deck itself. At first glance, it looks like a standard airfield at sea, but the geometry has been subtly, radically altered. The island, the command tower, where the bridge and flight deck control constitute the brain of the ship, has been moved. On the Nimitz class, the island is positioned further forward. On the Ford, it has been pushed 140 feet toward the stern. This might seem like an aesthetic choice, but in naval architecture, moving a structure that weighs hundreds of tons is never done for looks. This shift was dictated by the concept of the pit stop. On a traditional carrier, rearming and refueling an aircraft is a chaotic dance. Weapons elevators are located in the middle of the flight deck, meaning that when you bring up a bomb, you are blocking the very path the aircraft needs to taxi. It is a logistical bottleneck that caps the number of sorties, combat flights, a ship can launch in a day. By moving the island aft and creating a wider expanse of open deck space forward of the tower, the designers created a dedicated refueling and rearming area. This allows ordnance to be moved from the magazine to the aircraft wing without ever crossing the active taxi lines. The so what here is substantial. This layout alone is theoretically capable of increasing the sortie generation rate by 30% compared to the Nimitz. That means more bombs on target and more fighters in the air, simply by rearranging the furniture. However, moving the island was the easy part. The real revolution and the source of the deepest headaches lies deep within the hull. The beating heart of the CVN-78 is the Bechtel A-1B nuclear reactor. The Ford carries two of them. While the old A-4W reactors on the Nimitz were marvels of their time, the A-1B is a beast of a different nature. These reactors are smaller, require fewer sailors to operate, and yet they produce 25% more thermal energy. But the critical metric is not thermal energy, it is electrical generation capacity. The Ford has 3 times the electrical generation capacity of the Nimitz class. We are talking about enough electricity to power a medium-sized city, generated entirely independently at sea. This massive surplus of power was necessary because the Ford was designed to eliminate the one fluid that has defined naval aviation for a century: steam. On a Nimitz, when a pilot prepares to launch, a massive piston is driven down a track by high-pressure steam captured from the reactor loop. It is violent, it is jerky, and it puts enormous stress on the airframe of the aircraft. Steam catapults are also heavy, require miles of piping, and are difficult to maintain. If a steam pipe bursts, you have a lethal superheated hazard. The Ford does away with this entirely. It uses the electromagnetic aircraft launch system, known by the acronym EMALS. EMALS is the star of the show, and for a long time, it was the villain. Instead of a steam piston, the system uses a linear induction motor. Imagine a railgun, or the world's most powerful roller coaster launch system. A carriage sits in a trough in the deck, surrounded by electromagnets. When the command is given, massive pulses of electricity wave through the magnets, pulling the carriage forward with magnetic force. The benefits of this system are staggering on paper. Steam provides a dumb punch. It hits the aircraft hard at the start, and the force tapers off. EMALS is smart. It can monitor the weight of the aircraft and the speed of the carriage thousands of times a second, adjusting the magnetic force to provide a perfectly smooth, consistent acceleration. This smooth acceleration does more than just give the pilot a nicer ride. It extends the lifespan of the aircraft. The violent shock of a steam launch fatigues the metal of an F-35C or an FA-18 Super Hornet. Over thousands of launches, that stress adds up, leading to cracks and maintenance issues. EMALS is gentle. Furthermore, because it is adjustable, it can launch things that steam cannot. A steam catapult struggles to launch very light, unmanned drones because the minimum force is simply too high. It would rip the drone apart. EMALS can dial its power down to launch a light surveillance UAV, or dial it up to hurl a fully loaded bomber into the sky. This flexibility future-proofs the ship for the next 50 years of aviation development. But this overwhelming capability came with a hidden cost that the designers hadn't anticipated or perhaps underestimated. The so what of replacing steam with magnets is that you are now entirely dependent on software and clean power. In the early trials, EMALS failed. It failed often. There is a metric called mean cycles between critical failure. In the early days, the Ford could barely go a few hundred launches without the system glitching. unlike a steam catapult, which can often be fixed with a wrench and a sledgehammer, a failure in EMALS is a complex electrical fault. Even more concerning was the system's architecture. The 4 catapults draw energy from a shared energy storage group, massive flywheels and capacitor banks that store the energy from the reactors until it is needed for a launch. Initially, the system was designed such that if one catapult went down for maintenance, the power isolation required meant the other 3 might have to stop as well. This is the nightmare scenario in combat, a single electrical fault turning the world's most powerful warship into a floating airport with a closed runway. The Navy has spent years and millions of dollars isolating these systems to ensure redundancy, but it highlights the fragility of shifting from mechanical independence to integrated electrical dependence. The trouble did not stop at the front of the ship. If launching planes with magnets was hard, catching them with water twisters proved even harder. The Ford utilizes the Advanced Arresting Gear, or AAG. On a traditional carrier, when a plane lands, its tailhook grabs a wire. That wire is connected to a hydraulic engine below deck, essentially a giant piston moving through fluid that absorbs the energy of the landing aircraft. It is simple, proven, and robust. The AAG replaces this with water turbines and electric motors. The theory behind AAG is similar to EMALS. By using electric motors to resist the pull of the wire, the ship can finely tune the resistance. It can catch a heavy plane gently or a light drone without snapping the airframe. It reduces the shock on the aircraft and the pilot. However, the AAG suffered from terrible reliability issues during the ship's gestation. It was a classic case of over-engineering. The Navy took a system that worked, hydraulics, and replaced it with a system that required millions of lines of code to function. During initial testing, the failure rate was so high that critics argued the ship should be retrofitted with the old hydraulic engines. That was impossible. The ship was literally built around the new machinery. They had to make it work. The technical deep dive into the Ford cannot be complete without discussing the advanced weapons elevators. This sounds mundane. It is just an elevator, right? Wrong. These elevators are the arteries of the ship's lethality. On the Nimitz, the elevators that bring bombs from the deep magazines up to the flight deck are cable-driven mechanical systems. They are slow and they require open shafts that can act as conduits for fire and explosion if the ship is hit. The Ford uses electromagnetic elevators. They move on rails using linear synchronous motors, similar to maglev trains. These elevators can move 24,000 pounds of ordnance at 150 feet per minute. That is twice the speed and twice the capacity of the Nimitz elevators. They are also designed with watertight and flame-tight hatches that seal off the magazine from the hangar and the flight deck. This is a massive survivability upgrade. If a bomb detonates in the hangar, the fire cannot easily travel down the elevator shaft to the main magazine. However, the installation of these elevators became a national scandal. By the time the ship was commissioned, only a fraction of the 11 elevators were working. The tolerances required for the rails were so tight that the twisting and flexing of the ship at sea caused them to jam. It took years of post-delivery work to get all 11 functioning. This brings us to a crucial realization about the Ford class. It is a ship where the hull is just a wrapper for a massive integrated computer network. The radar system, the dual-band radar, was an ambitious attempt to combine 2 different radar bands, X-band and S-band, into a single system with flat phased array faces flush with the superstructure. The idea was to eliminate the spinning dishes of the past, reducing the ship's radar cross-section and maintenance needs. The DBR is incredibly powerful, capable of tracking incoming missiles, aircraft, and periscopes simultaneously with unprecedented fidelity. But it was so expensive and complex that the Navy actually canceled it for the future ships of the class. The USS Gerald R. Ford will be the only ship to carry this specific radar configuration, making it a unicorn in terms of maintenance and spare parts for the next 50 years. Knowing what you now know about its performance in the field, do you think the design trade-offs were worth it? Share your thoughts below. The operational reality of the USS Gerald R. Ford is a stark contrast to the sterile specifications of its design documents. When you talk to the sailors who live and work aboard CVN-78, you get a different perspective, one that focuses less on the electromagnetic wizardry and more on the quality of life. The Navy faced a recruitment and retention crisis, and the Ford was designed with the human element in mind. The berthing areas are a significant upgrade from the Nimitz. On older ships, sleeping quarters were often massive, 100-man bays that were noisy, smelly, and offered zero privacy. The Ford utilizes smaller berthing compartments, typically housing roughly 30 sailors. They are quieter, have better climate control, and are designed to allow for better rest. This matters because a tired crew is a dangerous crew. The reduction in manpower is another key operational difference. The Ford is designed to operate with approximately 600 to 800 fewer crew members than a Nimitz-class carrier. This reduction was achieved through automation. The A-1B reactors require less monitoring. The electric systems require less grease and wrench turning. Over the 50-year life of the ship, this reduction in personnel is expected to save the Navy $4 billion. However, there is a catch. In the Navy, manpower is also damage control. When a missile hits and fires break out, every sailor is a firefighter. By reducing the crew size, the Ford has fewer bodies to throw at a catastrophe. The designers argue that the automated fire suppression systems and better compartment isolation make up for this, but it remains a point of anxiety for traditionalists. The Blue Tile logistics system is another operational shift. The ship is designed with wider passageways and better connectivity to allow forklifts and automated robotic carts to move supplies. On a Nimitz, moving pallets of food or spare parts often involved human chains and backbreaking manual labor. On the Ford, the logistics are streamlined. This means the crew spends less time hauling boxes and more time maintaining their proficiency. It changes the rhythm of life at sea, reducing the grunt work that burns sailors out. Comparatively, how does the Ford stack up against its peers and rivals? The obvious comparison is the Nimitz class. A Nimitz is a proven warrior, a rugged, steam-belching heavyweight that has dominated the seas for decades. It is reliable because it is simple, or at least mechanically understandable. If the Ford is a Tesla, the Nimitz is a 1970 muscle car. The Tesla is faster and smarter, but if the computer crashes, you are stuck. The muscle car might leak oil, but it will get you there. The more pressing comparison is with the People's Liberation Army Navy of China, specifically the Type 003, the Fujian. The Fujian is China's first attempt at a supercarrier using electromagnetic catapults. It skips the steam era entirely, aiming to match the Ford's technology. However, the Ford has a significant advantage: nuclear power. The Fujian is conventionally powered, meaning it burns fuel to generate electricity. This places a massive logistical tether on the Chinese ship. It must be refueled constantly, and the energy required to charge its catapults burns through its fuel reserves rapidly. The Ford, with its A-1B reactors, has virtually unlimited range and power. It can sprint at over 30 knots for weeks without stopping. The Chinese ship may have the catapults, but it lacks the endurance. The true test of the Ford's operational reality came in the form of the full ship shock trials. This is a brutal exam where the Navy detonates 40,000 pounds of high explosives in the water near the ship. The goal is to see if the hull will crack and, more importantly, if the sensitive electronics will survive the seismic hammer blow. There were genuine fears that the delicate EMALS magnets, the maglev elevators, and the computer servers would shatter or desynchronize under the shock. When the charges went off, the ocean erupted. The ship shuddered violently, cameras rattled, and the crew braced for impact. The seismic data registered the event as a minor earthquake. And the result? The Ford shrugged it off. There were minor breakages, furniture, some pipe fittings, but the core systems held. The reactors did not scram, the catapults remained aligned. This was the vindication the program desperately needed. It proved that despite the digital fragility, the physical bones of the ship were tough enough for war. But we must address the sortie generation rate again, because this is the metric that justifies the $13 billion. In exercises, the Ford has demonstrated the ability to launch and recover aircraft faster than any ship in history. The wider flight deck and the pit stop arrangement work. Pilots report that the EMALS launch is so smooth it feels unnatural, but it allows them to take off with less physical strain. The turbulence behind the island is reduced, making landings safer. The ship is, purely as an airfield, a masterpiece. Yet the shadow of maintenance looms large. The proprietary nature of the systems means that the crew cannot always fix things themselves. They often rely on contractors and specialized tech support. In a high-intensity war in the Pacific, far from supply lines, this dependency could be fatal. If a circuit board in the AAG fries, you cannot just machine a new one in the shop. You need the spare part. The logistics chain for the Ford is as high-tech and fragile as the ship itself. As we move toward an assessment of the ship's legacy, we have to revisit the central conflict, the tension between innovation and reliability. The USS Gerald R. Ford was born out of necessity, but it was birthed through pain. The years of delays, the elevators that didn't move, the catapults that failed, these were the birth pangs of a new era. The Navy tried to invent too many things at once. They changed the hull, the reactor, the catapults, the arresting gear, and the radar, all in a single platform. This is known in acquisition circles as concurrent development, and it is usually a recipe for disaster. However, now that the systems are stabilizing, the brilliance of the gamble is becoming clear. The Nimitz class, for all its glory, is a dead end. It cannot host the laser defenses that will be required to stop hypersonic missiles. It cannot generate the power needed for the next generation of electronic warfare suites. The Ford is not just a ship, it is a power plant with a runway. It has a margin of growth that will keep it relevant into the 2070s. The legacy of the Ford will likely be similar to the F-35 Joint Strike Fighter. It was hated during development, mocked for its cost and its bugs, but eventually became the dominant platform in its field because nothing else could do what it does. The Ford brings a capability that no other nation possesses. It allows the U.S. Navy to launch heavier payloads with more variety at a higher rate, with limitless range. The price of this capability is a permanent shift in how the Navy operates. The era of the grease monkey mechanic keeping the ship running with duct tape and ingenuity is fading. The era of the systems administrator and the nuclear electrician is here. The Ford demands a smarter, more highly trained crew. It demands a flawless logistical tail. It is a high-performance machine that requires high-performance support. There is also a strategic psychological aspect to the CVN-78. When this ship arrives in a region, it projects a level of technological dominance that a steam carrier simply cannot match. It signals that the United States is willing to endure decades of development and spend unmatched fortunes to maintain maritime superiority. The visual of the Ford, with its sleek island and clean deck, is a statement of intent. But the final verdict on the Ford cannot be written until it sees combat. The shock trials proved it can take a hit, and the deployment exercises proved it can launch planes. But can it sustain high-tempo operations for months while under cyber attack with degraded systems and exhausted crews? The complexity of EMALS and AAG introduces unknown unknowns. We know how steam fails. We have 50 years of data. We do not yet know the myriad ways a linear induction motor can fail after 6 months of combat operations in a saltwater environment. The skeptics were right about the cost and the delays. $13 billion is an astronomical sum, enough to buy a fleet of smaller ships. But the proponents were right about the physics. You cannot cheat the laws of thermodynamics. If you want lasers, if you want railguns, if you want to launch the heavy drones of the future, you need the A1B reactor and you need electric distribution. The Nimitz could not do it. The Ford can. Ultimately, the USS Gerald R. Ford is a bridge to the future of naval warfare. It is an imperfect, expensive, and complex bridge, but it is the only one the Navy has. The teething troubles are the tuition fees paid for learning how to build the capital ships of the 21st century. As the subsequent ships of the class, the Kennedy, the Enterprise, the Miller, come online, they will benefit from the painful lessons learned on the 78. The Ford suffered so they could sail smoothly. It stands today not just as a warship, but as a testament to the sheer scale of American military ambition. It is a floating city of steel, silicon, and enriched uranium, designed to project power to the furthest corners of the Earth. It is quieter than its predecessors, but it carries a bigger stick. The silence on the bridge is not the silence of inactivity. It is the silence of a predator that no longer needs to roar to be heard. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching. The story of the Ford class is far from over. As it sails into the mid-century, it will likely undergo modifications we cannot yet imagine, hosting aircraft that haven't even been drawn on paper yet. But one thing is certain. The gamble has been made, the chips are on the table, and the USS Gerald R. Ford is now the standard by which all other blue water naval power will be measured. The age of steam is dead. The age of the electric carrier has begun.